On May 10th, 2024, while you were scrolling through photos of stunning green and purple auroras, Earth's magnetic shield was being crushed like a soda can. Scientists measured an 80% compression of our planet's protective barrier. The most beautiful light show in living memory was actually a distress signal. And here's what nobody told you. It took 5 days for our magnetic field to recover. 5 days when it should have taken 2. As we head toward the next solar peak, scientists are warning that our weakened magnetic field and total dependence on technology have created a perfect storm. One direct hit from a Carrington-level event could permanently fry the global power grid, plunging modern civilization into a years-long darkness from which we might never recover. Subscribe and follow along, because the cosmic timing of what's unfolding above your head is more sinister than anyone's admitting publicly. The night sky over Montana turned green, then purple, then crimson. People pulled over on highways. They pointed. They filmed. They gasped at the most spectacular light show most of them would ever witness. What they didn't know, what almost no one knew as they stood there, in awe, was that directly above their heads, Earth's magnetic shield was being crushed like an aluminum can in a vise. May 10th, 2024. The date doesn't sound apocalyptic, does it? It sounds like a Friday in spring. But on that date, our planet experienced the most violent magnetospheric compression ever recorded in the modern satellite era. Not the biggest solar flare, not the fastest coronal mass ejection. The most violent compression of the invisible force field that stands between us and a universe trying very hard to kill us. Let me explain what actually happened up there while you were staring at those pretty lights. Earth sits inside something called the plasmasphere. Think of it as the inner shock absorber of our magnetic defense system, a donut-shaped region of dense plasma that surrounds our planet like a cushion. Normally, this boundary extends outward to about 44,000 kilometers. That's roughly 3 times the diameter of Earth itself. It's our buffer zone, our crumple zone, the thing that takes the first punch when the sun throws one. On May 10th, that boundary was forced inward to under 10,000 kilometers. The plasmasphere compressed by roughly 80%. Imagine your airbag deflating to 1/5 its normal size right before impact. That's what happened to Earth's magnetic airbag while we were all taking selfies with the Aurora. Now, here's where it gets truly unsettling. After a major geomagnetic storm, the plasmasphere typically recovers in 24 to 48 hours. The plasma refills. The boundary re-expands. Everything goes back to normal. Except this time, it didn't. This time, it took 5 days. 5 full days for Earth's magnetic shield to limp back to something resembling its pre-storm configuration. Why does this matter? Because recovery time tells us something that peak intensity doesn't. It tells us about resilience. It tells us about structural integrity. If you get punched in the face and it takes 5 times longer than usual to stop seeing stars, that's not just a harder punch. That's a sign that something about you has fundamentally changed. The scientists noticed. Oh, they noticed. In the weeks following the storm, statements from NASA's heliophysics divisions became unusually careful. The European Space Agency's swarm mission scientists started using phrases like unprecedented plasmaspheric dynamics and unexpectedly prolonged recovery phase. NOAA's Space Weather Prediction Center updated their internal models. These are not institutions prone to hyperbole or panic. These are the people who watch the sun for a living, who have seen dozens of major storms, who know the difference between a bad day and a paradigm shift. A new term started appearing in preliminary research papers, whispered in conference hallways, mentioned in internal emails: magnetic fatigue. The idea that Earth's magnetic field, like any stressed material, might accumulate damage over time, that repeated hammering might leave it less able to bounce back. That we might be witnessing not just a strong storm, but the slow-motion failure of a system we've always assumed was indestructible. Let me be crystal clear here. This is an emerging hypothesis, not scientific consensus. The data is still being analyzed. The mechanisms are still being debated. But the fact that serious scientists are even discussing the possibility of cumulative magnetic damage should make your skin crawl just a little bit. Because here's what we know for certain. Earth's magnetic field didn't snap back into place like it always had before. It didn't bounce. It crawled. It struggled. And while it was struggling, every satellite in low Earth orbit, every GPS receiver, every power grid, every piece of technology that depends on a stable magnetosphere was more vulnerable than it had been in recorded history. The auroras were beautiful. No one's arguing that. But beauty is often a warning sign in nature. Bright colors on a frog mean poison. A mushroom that glows means don't eat it. And auroras at latitudes where they shouldn't be, that means the shield is down. So here's the question that kept me awake for weeks after May 2024. What if the storm didn't break our shield? What if it simply revealed that our shield was already broken? What if we've been living under a failing defense system and didn't realize it until something hit us hard enough to show the cracks? And here's the truly terrifying part. That wasn't even a worst-case scenario. That was a G5 storm. The highest category on our scale, yes. But it wasn't the biggest the sun can throw. It wasn't a Carrington event. It wasn't the cosmic equivalent of a direct hit. It was a glancing blow, a warning shot, a preview, and our planet barely handled it. Let me tell you what this documentary is not about. This is not about the sun suddenly becoming more dangerous. This is not about solar cycles going haywire or our star entering some new phase of violence. The sun is doing exactly what it's always done. The sun is fine. We are not fine. The core claim here, the thing I need you to understand before we go any further, is about timing. It's about convergence. It's about two slow-moving catastrophes meeting each other at precisely the worst possible moment in human history. On one side, we have Earth's magnetic field, which has weakened by 10 to 15% over the past 200 years. That's the conservative estimate. Some regions have weakened by much more. The field isn't collapsing, not yet, but it's definitely not what it used to be. There's a clear asymmetry in field strength across hemispheres. The protection you get standing in Sao Paulo is measurably different from the protection you get standing in Oslo. On the other side, we have Solar Cycle 25. And Solar Cycle 25 is not playing by the rules. It's stronger than predicted. It arrived earlier than models suggested. It's producing more frequent high-energy events than the previous few cycles. Why? Because the forecasting models were based on recent solar behavior, and recent solar behavior was unusually quiet. We built our predictions on an anomaly, and then acted surprised when the sun returned to historical norms. We underestimated the sun because we got used to it being gentle. Now, here's where the timing gets truly sinister. As Solar Cycle 25 approaches its maximum, which is happening right about now, we are more dependent on electromagnetic infrastructure than at any point in human existence. Our power grids are not just bigger than they were 50 years ago. They're more interconnected, more complex, more optimized for efficiency rather than resilience. High-voltage transformers, the kind that step down power from transmission lines to distribution networks, are custom-built pieces of equipment. They're not sitting in warehouses waiting to be installed. They take months to manufacture. Some take over a year. And they're designed to last for decades under normal conditions. They were not designed for geomagnetic storms. When a major coronal mass ejection hits Earth's magnetosphere, it induces currents in long conductors. Power lines are very long conductors. These geomagnetically induced currents flow into transformers. Transformers are designed to handle alternating current at specific frequencies. They are not designed to handle massive direct current surges that last for hours or days. The longer the disturbance lasts, the more likely transformers are to overheat, saturate, and fail catastrophically. Duration matters more than intensity for grid damage. A moderate storm that lasts 3 days can do more harm than a massive storm that lasts 3 hours. This is why comparisons to the Carrington event are both useful and frustrating. The Carrington event of 1859 was the largest geomagnetic storm in recorded history. Telegraph systems worldwide sparked and caught fire. Operators received shocks. Some telegraph lines continued working even after being disconnected from their batteries, powered purely by the currents induced by the storm. It was spectacular. It was unprecedented. And we have no idea what it would do to a modern power grid because we've never tested one under those conditions. We can model it, we can simulate it, we can make educated guesses, but we don't actually know. What we do know is that a storm even half the intensity of the Carrington event hitting today would likely cause widespread transformer failures. Recovery times would be measured in months or years, not days or weeks, and that's not speculation. That's the conclusion of multiple government-commissioned studies, industry analyses, and academic research. Here's the probability versus impact framework you need to understand. The probability of a Carrington-level event in any given year is low, very low, somewhere between 0.5 and 1%, depending on whose estimate you trust. But the impact of such an event is catastrophic, not inconvenient, not disruptive, catastrophic, civilization-altering. The kind of event that reshuffles the deck entirely. We're very bad at thinking about low probability, high impact events. Our brains aren't wired for it. A 1% chance feels like never. It feels like someone else's problem. It feels like something we can safely ignore because it probably won't happen to us. But 1% per year is not never. Over a decade, that's nearly a 10% chance. Over a century, it's not a question of if, but when. And we're heading into that gamble with a weakened magnetic field and an infrastructure that's more vulnerable than it's ever been. The sun doesn't need to be stronger than it was during the Carrington event. It just needs to be well-timed. It needs to throw a punch while our guard is down, while our shield is compromised, while we're looking the other way. But here's the thing that kept me digging deeper into this story. The thing that turned a concerning scientific trend into an obsession. The sun wasn't the strangest thing we observed in 2024. Not even close. Because while we were watching solar activity and measuring magnetic field strength and worrying about transformers, something else was happening in near-Earth space. Something the models didn't predict. Something that suggests our understanding of how all these systems interact might be fundamentally incomplete. And that's where this story gets really weird. Let's go back to that 5-day recovery period after the May storm, because I glossed over just how strange this actually was. The plasmasphere is supposed to refill through a well-understood process. Plasma from Earth's ionosphere flows upward along magnetic field lines. Cooler, denser plasma gradually replaces the hot, turbulent plasma ejected during the storm. The boundary re-expands. Balance is restored. We've observed this cycle dozens of times. We have models for it. We thought we understood it. 5 days breaks all of those models. Plasmasphere recovery should work like this. Imagine a bathtub that's been violently drained. Once the turbulence stops, you turn the faucet back on, and the tub refills at a predictable rate based on water pressure and drain size. Simple fluid dynamics. But what if you turn on the faucet and the tub refills at 1/5 the expected rate? That suggests something about the system has changed. Either the source is depleted, or the pathway is blocked, or the tub itself has somehow been altered. Scientists are now considering several competing hypotheses, and I want to be very clear that these are hypotheses, not confirmed theories. One possibility is plasma density depletion. Maybe the storm ejected so much material from the inner magnetosphere that there simply wasn't enough plasma available in the ionosphere to refill at normal rates. Another possibility involves magnetic field line stretching memory. The idea that field lines, once severely distorted, don't snap back to their original configuration, but retain some memory of the disturbance. A third, more unsettling possibility is cumulative storm damage. The notion that each major geomagnetic storm leaves the magnetosphere slightly less capable of recovering from the next one. Any of these explanations would require us to revise our understanding of near-Earth space dynamics. All of them suggest we're missing something fundamental. But wait, it gets weirder. During and after the May storm, satellite instruments detected something unexpected in Earth's ionosphere. Ionized metals, primarily from micrometeorites that constantly rain down on our planet, are normally confined to narrow bands near the poles. They're part of the natural atmospheric chemistry up there, nothing unusual. Except in late May, these ionized metal layers were observed drifting toward lower latitudes, spreading out, behaving in ways they weren't supposed to behave. This surprised scientists for a very specific reason. Ionized metals change how radio waves propagate through the atmosphere. They affect GPS signal reliability. They interfere with high-frequency communications. And they're doing all of this in regions where they're not supposed to exist in meaningful concentrations. Aviation systems rely on precise GPS timing. Military communications depend on stable ionospheric conditions. Financial networks use GPS clocks to timestamp transactions. All of these systems are calibrated for normal ionospheric behavior. We no longer have normal ionospheric behavior. The models didn't predict this. The simulations didn't include this variable. And that's the core issue here, the thing that keeps me up at night more than any single data point. Our models of how near-Earth space responds to solar storms are failing. Not catastrophically failing, not yet, but failing nonetheless. Predicting 90% of the outcome is impressive, until you realize that the other 10% includes all the things that could actually kill us. Modeling failure is more dangerous than we typically acknowledge, because models aren't just academic exercises. They're the basis for policy decisions. They inform how much money gets allocated to grid hardening. They determine warning thresholds for satellite operators. They shape public perception of risk. When your models consistently underpredict the severity and duration of space weather effects, you end up with a civilization that's systematically underprepared for the reality it's about to face. And here's the truly chilling possibility that some researchers are beginning to whisper about. What if extreme geomagnetic storms don't just temporarily disturb near-Earth space? What if they permanently alter it? What if each major event shifts the baseline conditions, making the environment progressively less stable, less predictable, less safe? We've never had the instrumentation to test this hypothesis over multiple solar cycles. We've never watched the same region of space, with the same level of precision, through enough major storms to know whether the system fully recovers or slowly degrades. We're running the experiment right now. We're the experiment. The May 2024 storm revealed something essential about our predicament. It revealed that our planet's protective systems are more fragile, more dynamic, and more poorly understood than we'd assumed. It revealed that the gap between our models and reality is growing. And it revealed that we're heading into the peak of solar cycle 25 with less protection and less understanding than we thought we had. This was all with Earth's magnetic shield still mostly intact, still functioning, still providing the majority of the protection it's supposed to provide. So here's the question that haunts every conversation I've had with space weather researchers. What happens when the shield itself starts to fail? Okay, we need to talk about magnetic pole shifts. And I know what you're thinking. I know this is where the documentary loses credibility, where we veer off into pseudoscience and conspiracy theories and people selling survival bunkers. But here's the uncomfortable truth. Scientists have been avoiding this conversation for so long, have been so worried about being lumped in with the doomsday crowd, that the actual science of geomagnetic reversals has been systematically undercommunicated to the public. So let's be extremely clear about what scientists actually agree on. Earth's magnetic poles move. They always have. The North Magnetic Pole is currently racing across the Arctic at about 55 kilometers per year, which is unusually fast. The South Magnetic Pole is also moving, though somewhat more slowly. This is normal. This is expected. Pole movement by itself is not alarming. Earth's magnetic field also weakens and strengthens over time. Over the past 200 years, it has weakened by 10 to 15% globally, with some regions experiencing much more dramatic declines. This is measurable. This is verified by multiple independent sources. This is not controversial science. Earth's magnetic field has also completely reversed many times throughout geological history. North becomes south. South becomes north. These reversals happen roughly every 200,000 to 300,000 years on average, though the timing is extremely irregular. The last full reversal was about 780,000 years ago. We're overdue, statistically speaking, but statistics over geological timescales are meaningless for predicting events within human lifetimes. Here's what's genuinely weird and worth paying attention to. The South Atlantic anomaly, a region where Earth's magnetic field is significantly weaker than surrounding areas, is growing. It's expanding westward over South America. Satellites passing through this region experience higher radiation exposure. The International Space Station has to shut down non-essential systems when passing through it. This anomaly might be a normal fluctuation, or it might be an early sign of field instability. Scientists genuinely don't know. Rapid pole drift acceleration is another verified anomaly. The North Magnetic Pole's movement has accelerated dramatically over the past few decades. Models have had to be updated more frequently than expected. Again, this could be normal variation, or it could indicate something more fundamental happening in Earth's core. The honest answer is, we don't have enough long-term data to say. Now, here's where we move from verified facts into clearly labeled speculation. Some researchers have suggested that we might be entering an unstable geomagnetic configuration. Not a full reversal necessarily, but a period of rapid change, weakening, and unpredictability. A geomagnetic excursion, in technical terms. During such events, which can last thousands of years, the field's strength can drop significantly, and the pole positions can wander chaotically before either reversing or settling back. The counter-arguments to pole shift panic are entirely valid. Pole reversals take thousands of years to complete. Life on Earth has survived them before. There's no evidence of mass extinctions correlated with reversals. The field doesn't disappear entirely during a reversal. It just becomes more complex, multipolar, with multiple north and south poles instead of a clean dipole. But here's the rebuttal that deserves serious consideration. Human civilization has never experienced a geomagnetic reversal, or even a major excursion. We've never tried to maintain a technological society while Earth's magnetic field reorganizes itself. We've never had billions of people dependent on satellite navigation and electrical grids during a period of geomagnetic chaos. Life survived previous reversals, sure, but life is resilient. Civilization is not. Civilization is fragile. Civilization depends on infrastructure, supply chains, just-in-time delivery, GPS-guided navigation, and a power grid that assumes magnetic conditions will remain within certain stable parameters. The deep Earth mystery at the heart of all this is genuine and profound. Earth's magnetic field is generated by a dynamo effect in the liquid iron outer core. We understand the basic principle. Moving molten metal generates electric currents, which generate magnetic fields, which influence the metal's motion, creating a self-sustaining system. But the details of how this works, how it remains stable, and why it sometimes becomes unstable are poorly understood. We can't exactly send probes down there to measure it directly. We're inferring the behavior of a churning metallic ocean 3,000 kilometers beneath our feet, based on surface measurements and computer simulations. It's an educated guess. A very educated guess. Based on physics and seismology and centuries of magnetic observations. But it's still a guess. So here's the unsettling question that ties all of this together. What if the weakening we're observing isn't linear? What if it's stepwise? What if Earth's magnetic field can maintain a certain configuration for a long time, then suddenly reorganize, then stabilize again at a weaker level? What if we're approaching one of those transition points right as solar cycle 25 is peaking? Even if the science remains uncertain, even if we can't predict exactly when or how the field might change, the consequences are not uncertain. A weaker magnetic field means more radiation reaches Earth's surface, more cosmic rays, more solar particles, more damage to satellites, electronics, biological systems, and the thin layer of atmosphere that keeps us alive. We might have centuries before any of this becomes critical. We might have decades. We might be living through the early stages of it right now and not realize it until historians look back and connect the dots. Either way, the story doesn't end with physics and planetary dynamics, because the real question isn't what happens to Earth's magnetic field. The real question is what happens to us. Governments don't like talking about worst-case scenarios, not because they're hiding conspiracies or suppressing information, but because worst-case messaging is politically radioactive. Tell people that a solar storm could knock out power for months. And what do you get? Panic, bank runs, hoarding, supply chain disruptions caused by fear of supply chain disruptions. The psychological and economic damage from the warning can exceed the damage from the event itself if the event never materializes. History has taught us this lesson repeatedly. In 1973, the oil embargo created fuel shortages, but the panic buying created worse shortages than the actual supply reduction warranted. In 2020, early pandemic warnings led to toilet paper hoarding that had nothing to do with the actual threat. People are terrible at calibrating their responses to abstract dangers. We either ignore them completely or overreact catastrophically. There's very little middle ground. So instead, official communication focuses on preparedness, resilience, and reassurance. We're monitoring the situation. We have protocols in place. The risk is manageable. And to be fair, for most space weather events, this is absolutely true. The vast majority of solar storms cause minor disruptions at worst. Satellites reboot. GPS accuracy decreases temporarily. Radio communications experience interference. Life goes on. The daily reality of space weather is mundane. Solar flares happen all the time. Small coronal mass ejections are routine. Geomagnetic fluctuations occur constantly, and we handle them. Satellite operators adjust orbits. Power companies monitor grid loads. Airlines reroute polar flights when radiation levels spike. The system works. The protocols work. Most of the time, space weather is a nuisance, not a catastrophe. But there's a specific scenario that keeps infrastructure experts awake at night, and it's called black start. When a power grid goes down, you need external power to restart it. Generators need electricity to begin generating electricity. It's a bootstrapping problem. Normally, this isn't an issue because regional grids can borrow power from neighboring grids to restart. But if a geomagnetic storm takes down multiple interconnected grids simultaneously, There's no external power available. You're stuck. And here's the nightmare detail. High voltage transformers, the critical components most vulnerable to geomagnetically induced currents, can take 6 months to 2 years to manufacture and install. Let me explain why transformers are the critical vulnerability. These aren't small devices. High voltage transformers can weigh hundreds of tons. They're custom designed for specific grid configurations. They're built to order, often overseas, with lead times measured in months, even under normal conditions. And they're expensive. A single large transformer can cost millions of dollars. Utilities don't keep many spares sitting around because storing a 100-ton piece of specialized equipment isn't exactly cost-effective. During a severe geomagnetic storm, these transformers can fail in several ways. The most common is overheating from geomagnetically induced currents that cause internal components to saturate. Once a transformer fails catastrophically, it's not repairable. It's scrap metal. You need a replacement. And if hundreds of transformers fail simultaneously across a large geographic area, you're looking at recovery times that stretch into years, not months. The EMP Commission, a congressional advisory panel that studied electromagnetic threats to critical infrastructure, published findings that are somehow both alarming and ignored. Their conclusion was that a severe geomagnetic storm affecting the eastern United States power grid could leave tens of millions without power for months or longer. The cascading failures would be catastrophic. Water treatment plants stop operating. Hospitals run through backup generator fuel in days. Food refrigeration fails. Supply chains collapse. Communication networks go dark once cell tower batteries die. They also estimated casualty figures. Not from the storm itself, obviously. The storm doesn't directly hurt anyone, but from the collapse of systems that keep modern society functioning. Within a year of a major grid failure, they estimated that up to 90% of the population in affected areas could die from starvation, disease, and societal breakdown. 90%. Let that number sit with you for a moment. The official reports exist. They're publicly available. They outline these scenarios in bureaucratic language that somehow makes civilizational collapse sound like a minor policy concern. And yet, the level of actual preparation, actual grid hardening, actual stockpiling of replacement transformers remains woefully inadequate because preparation is expensive and disasters are improbable, and political systems are much better at responding to crises than preventing them. There's a fundamental mismatch between political timescales and disaster timescales. Politicians operate on election cycles. 2 years, 4 years, maybe 6. Disasters operate on geological and astronomical timescales. Decades, centuries, millennia. Asking a politician to spend billions of dollars today to prevent a disaster that might happen in 20 years, or 50 years, or never in their lifetime, is asking them to commit political suicide. The voters won't reward them for it. Their opponents will attack them for wasting money. And if the disaster never happens, history won't remember their foresight. There's a contrast worth noting between official reassurance and internal planning scenarios. Public-facing statements from NOAA and NASA emphasize monitoring capabilities and international cooperation. Internal planning documents, the ones prepared for emergency management agencies, paint a much darker picture. They discuss recovery timelines, not in days, but in seasons. They model population displacement. They consider martial law, not because these agencies are pessimistic, but because planning for the worst is literally their job. I've read some of these internal documents. They're chilling in their matter-of-fact assessment of civilizational collapse. They discuss which cities would be prioritized for power restoration, which populations would be evacuated, how to maintain order when food supplies run out, how to prevent mass migration from overwhelming functional areas. These aren't conspiracy theories. These are contingency plans prepared by serious professionals doing serious work. This isn't conspiracy. This is bureaucracy doing exactly what it's supposed to do, preparing for low probability, high impact events while trying not to terrify the population in the process. But here's what makes modern infrastructure uniquely vulnerable: cascading failures. Our systems are interconnected in ways that amplify rather than dampen shocks. Power depends on water for cooling. Water treatment depends on power for pumps. Food distribution depends on both power and communication networks. Hospitals depend on all three plus fuel deliveries, plus pharmaceutical supply chains. When one system fails, it doesn't just affect that system. It triggers failures in every system connected to it. This interconnectedness is normally a strength. It's what makes modern civilization so efficient, so capable, so productive. But it's also what makes us fragile. A power outage doesn't just mean lights go out. It means water stops flowing because pumps need electricity. It means sewage backs up because treatment plants can't operate. It means gas stations can't pump fuel even if they have fuel in their tanks. It means grocery stores can't refrigerate food. It means hospitals can't operate equipment. It means communication networks fail once backup batteries drain. Recovery timelines matter more than initial damage because humans are remarkably good at enduring short-term disasters. We can survive without power for days or even weeks if we know it's temporary. We have emergency supplies, backup plans, community resilience. But when the timeline stretches into months, when the damage isn't fixable with local resources, when the cascade of failures creates a new equilibrium far below normal functioning, that's when civilization starts to fray. Studies of past disasters show that social cohesion holds for about 3 to 5 days without basic services. After that, you start seeing breakdowns, looting, violence, desperate people making desperate decisions. And this is with the knowledge that help is coming, that the disaster is temporary, that normalcy will return. Imagine a scenario where there's no clear timeline for restoration, where the damage is so widespread that help isn't coming, where everyone realizes simultaneously that this isn't temporary. There's an uncomfortable conversation about information suppression versus panic prevention that needs to happen. How much should governments tell the public about existential risks? Is it ethical to withhold information about potential catastrophes because people might make irrational decisions if they knew? Or is it ethical to keep people informed, even if that information causes anxiety and possibly harmful behavior? There's no easy answer. Both positions have merit. Both have been proven correct in different contexts. The argument for transparency is compelling. People deserve to know about threats that could affect their survival. They deserve the opportunity to prepare, to make informed decisions about where to live and how to structure their lives. Withholding information is paternalistic. It treats citizens like children who can't handle difficult truths. The argument for controlled messaging is equally compelling. Panic can kill more people than the disaster itself. Bank runs can destroy economies. Mass evacuations can cause traffic deaths and overcrowding disasters. Sometimes the responsible thing is to manage information carefully, to communicate risk without triggering irrational fear. What's clear is that our modern civilization has been optimized for efficiency rather than resilience. Just-in-time delivery means minimal stockpiles. Interconnected grids mean maximum coverage at minimum cost. Specialized infrastructure means incredible capability with single points of failure. We've built a system that works brilliantly under normal conditions and catastrophically fails under exceptional ones. We've eliminated redundancy because redundancy is expensive. We've eliminated stockpiles because storage costs money. We've eliminated isolation between systems because integration is more efficient. Every optimization that made our civilization more productive also made it more fragile. And we've done this during a period of exceptional geomagnetic calm. The past several decades have been unusually quiet in terms of major space weather events. We designed our infrastructure during peacetime and assumed peacetime would continue forever. The last truly severe geomagnetic storm was in 1989, and it knocked out power to 6 million people in Quebec for 9 hours. That was considered catastrophic at the time. But the grid in 1989 was less interconnected, less dependent on high voltage transmission, less optimized. A similar storm today would cause far more damage because our infrastructure has evolved in ways that increased vulnerability while increasing capability. But the story doesn't end with helplessness and existential dread, because humans are remarkably good at adapting when they actually focus on a problem. We have technologies now that didn't exist during previous solar cycles. We have capabilities that could, potentially, change the equation. The question is whether we'll deploy them in time. In 2024 and 2025, something interesting happened in the world of space weather forecasting. Artificial intelligence algorithms, trained on decades of solar observation data, started detecting patterns that human researchers had missed. Machine learning models began predicting coronal mass ejections hours earlier than traditional physics-based models. AI systems identified subtle magnetic complexity patterns on the solar surface that correlated with major flare activity. This is genuinely exciting. This represents real progress. But we need to be extremely careful about what we claim AI can actually do here. Traditional space weather forecasting relies on physics-based models. You measure solar magnetic fields, track sunspot development, monitor coronal holes, and use equations that describe plasma behavior to predict what happens next. These models work reasonably well. They give us hours to days of warning before a coronal mass ejection reaches Earth. But they struggle with complexity. They miss subtle precursors. They fail to capture the chaotic dynamics of magnetic reconnection and plasma turbulence. The problem is that the sun is fundamentally chaotic. Solar plasma doesn't follow simple rules. Magnetic field lines twist, reconnect, and snap in ways that are incredibly difficult to model mathematically. You're trying to predict the behavior of a roiling ball of electrically charged gas that's 1.4 million kilometers across, where temperatures vary by millions of degrees, where pressures are beyond anything we can replicate on Earth, and where magnetic fields are so complex they make terrestrial magnetism look like a simple bar magnet. Physics-based models do their best. They've gotten better over decades. They can predict slow-moving coronal mass ejections reasonably well, but fast CMEs, the really dangerous ones that cross the distance from Sun to Earth in 15 to 18 hours instead of 2 to 3 days, those still catch us by surprise more often than we'd like to admit. Machine learning takes a different approach. Instead of encoding physics equations, you feed the algorithm massive amounts of historical data and let it find patterns. Show it 1,000 examples of what the sun looked like before a major flare, and it learns to recognize those configurations. The advantage is that AI can detect correlations humans never would have noticed. The disadvantage is that correlation isn't causation. AI can tell you that this solar magnetic configuration has preceded flares 85% of the time. It can't tell you why. And that's both the promise and the peril of AI forecasting. It works until it doesn't. It identifies patterns until it encounters a pattern it's never seen before. And with something as variable as solar activity, as chaotic as plasma physics, there will always be configurations the training data never included. Recent AI-driven systems can now detect CME precursors like helmet streamer distortions and pre-eruption dimming in coronal imagery. They can analyze magnetic complexity patterns, specifically measurements like magnetic polarity, inversion lines, and neutral line length that correlate with flare probability. They're getting better at this. Incrementally, measurably better. Some systems are now achieving prediction accuracy rates above 70% for major solar flares, which is significantly better than older models. But 70% means you're wrong 3 times out of 10. And when the stakes are global power grids and satellite infrastructure worth hundreds of billions of dollars, being wrong 3 times out of 10 is still terrifying. There's another challenge with AI forecasting that doesn't get discussed enough. Machine learning models are black boxes. You input solar imagery and magnetic field data. The algorithm processes it through layers of neural networks, and it outputs a probability of flare activity. But you can't easily trace the reasoning. You can't ask the AI to explain exactly which features it's weighting most heavily. This makes it difficult for human forecasters to verify the predictions or to understand when the model might be operating outside its competency. Traditional physics models are transparent. You can examine the equations, check the assumptions, understand exactly why the model predicted what it did. AI models are opaque. They work when they work, but understanding why they work is much harder. But here's the critical limitation that applies to both approaches. Prediction is not prevention. Even if we had perfect forecasting, even if we could predict every solar storm a week in advance with 100% accuracy, that doesn't protect the power grid. Warning time is still measured in hours or days at best. That's enough time to put satellites in safe mode, to issue alerts to power companies, to suspend certain operations. It's not enough time to harden infrastructure, replace vulnerable transformers, or fundamentally change our level of protection. Grid hardening, the actual physical modification of power infrastructure to withstand geomagnetically induced currents, is possible. You can install blocking devices that prevent direct current from flowing into transformers. You can add redundancy. You can create isolated grid sections that can be shut down and restarted independently. All of this is technically feasible. Some of it is even cost-effective when you factor in the risk reduction. Countries like Finland have invested heavily in grid resilience because they're at high latitudes where geomagnetic disturbances are more common. They've installed protective devices on transformers. They've created redundant pathways for power distribution. They've essentially accepted that space weather is a regular threat and planned accordingly. It works. Their grids are measurably more resilient. But it's not happening fast enough in most places. The investment required is massive. The political will is lacking. And critically, you're asking utilities to spend billions of dollars today to prevent a disaster that might happen tomorrow or might not happen for decades. From a purely economic perspective, from a quarterly earnings perspective, from a political re-election cycle perspective, it's a terrible investment. The return on investment only becomes clear after the disaster you prevented, and proving you prevented something is impossible. There's a fascinating and unsettling question emerging in discussions about AI-powered grid management. Could AI one day trigger automatic grid shutdowns? Imagine a system that detects an incoming CME, calculates the probable geomagnetic disturbance, and automatically disconnects vulnerable grid sections before the storm arrives. No human decision required. Just algorithms protecting infrastructure based on real-time threat assessment. The technical capability will probably exist within the next decade. The sensors are there. The data processing is there. The machine learning models are rapidly improving. Connecting these systems to actual grid control infrastructure is conceptually straightforward, but the ethical and political questions are much harder. Who decides when to pull the plug? What threshold of risk justifies shutting down power to millions of people? What if the AI is wrong? What if the storm turns out to be weaker than predicted, and you've just caused a blackout for nothing? What if it's stronger, and you didn't shut down enough of the grid? These aren't abstract thought experiments. These are decisions that will need to be made, possibly soon, by people who are not prepared to make them. Utility executives are not typically trained in space physics. Politicians are not experts in machine learning reliability. And yet, These are the people who will ultimately control whether AI systems are given the authority to shut down critical infrastructure based on predictions about solar activity. There's also the uncomfortable question of liability. If an AI system predicts a major storm, triggers automatic shutdowns across multiple states, and the storm turns out to be mild, who's responsible for the economic damage? The utility company? The software developer? The government agency that certified the system? If the AI fails to predict a storm that destroys transformers, who's liable for not shutting down when they could have? We're entering uncharted legal and ethical territory here. And we're doing it quickly, driven by technological capability rather than careful societal consideration. And here's the sobering reality check. Even perfect forecasting wouldn't fix the structural weakness. The May 2024 storm was predicted. Space weather agencies saw it coming. Warnings were issued. Precautions were taken. And Earth's plasmasphere still got crushed. The system still took 5 days to recover. The models still failed to predict the ionospheric metal anomalies. We knew the punch was coming and still got hurt. Better forecasting helps. It absolutely helps. It gives us time to minimize damage, to protect the most critical systems, to prepare for disruptions. It lets satellite operators turn spacecraft away from the sun, shut down sensitive instruments, boost orbits slightly to reduce atmospheric drag during geomagnetic storms. It gives power companies time to reduce grid loading, to disconnect non-essential systems, to prepare repair crews. All of this is valuable. All of this saves money and prevents damage, but it doesn't change the fundamental equation. It doesn't strengthen Earth's magnetic field. It doesn't make our infrastructure less vulnerable. It doesn't prevent the disaster. It just gives us a chance to duck. And ducking only works if the punch isn't too powerful and doesn't last too long. If the geomagnetic disturbance persists for days, if multiple CMEs arrive in succession, if the solar wind remains turbulent for weeks, no amount of forecasting will prevent damage. You can only keep critical systems in safe mode for so long before you start losing capabilities you can't afford to lose. Technology might buy us time. AI might give us better warnings, but neither addresses the underlying convergence of a weakening planetary shield and a solar cycle that refuses to cooperate with our wishful thinking. We're treating the symptoms while ignoring the disease. We're building better smoke detectors while the house's foundation crumbles. And if you think the stakes are high for our civilization, wait until you zoom out. Because our sun, despite everything we've discussed, despite all its violence and unpredictability, is actually one of the calmer stars in the galaxy. We know this because we've been watching other stars, and what we've seen should terrify you. In 2012, astronomers observing a sun-like star about 115 light-years away detected a super flare. The energy released was equivalent to about 10 billion times the energy of the largest solar flare ever recorded from our sun. This wasn't an isolated event. Over the past decade, we've observed hundreds of super flares on stars that are, by all measurements, extremely similar to our sun. Same mass, same age, same spectral classification, same everything. The phenomenon is verified. It's not controversial. Sun-like stars are capable of producing flares orders of magnitude more powerful than anything we've seen from our own star in recorded history. Let me put that scale into perspective for you. The most powerful solar flare we've ever directly measured was an X-28 flare in 2003. It was enormous. It disrupted satellite communications. It caused radiation storms. It was, by our standards, a monster. Now, multiply that by 10 billion. The energy release from these stellar superflares is so extreme that if our sun produced one, it would strip away significant portions of Earth's atmosphere. The radiation dose at ground level would be lethal. Every satellite in orbit would be instantly fried. the geomagnetic storm would be beyond anything our infrastructure could possibly withstand. We've now cataloged superflares on stars that are nearly identical twins to our Sun. G-type main sequence stars, similar metallicity, similar rotation rates, similar ages. These aren't exotic stellar objects. These aren't dying stars or binary systems or anything we could dismiss as fundamentally different from our own solar environment. These are stars that, if you traveled to their planetary systems, you might briefly mistake for home, and they're producing events that would end our civilization in hours. Now, before you panic completely, let me be clear about what this does and doesn't mean. There is no evidence that our Sun is about to produce a superflare. There's no indication that such an event is imminent, or even likely within our lifetimes. The frequency of superflares on Sun-like stars appears to be very low, possibly once every few thousand years per star. Our Sun has shown no signs of the kind of magnetic activity that would precede such an event. The specific conditions that trigger superflares are still being studied, but they seem to require magnetic field configurations that our Sun hasn't displayed in the time we've been observing it. Statistical analysis suggests that younger, faster rotating Sun-like stars are more prone to superflares. Our Sun is middle-aged and relatively slow rotating, which probably puts us in a lower risk category. Probably. The uncertainty here is maddening because we're working with incomplete data. We've only been observing other stars with enough precision to detect superflares for about 2 decades. That's not nearly enough time to establish reliable statistics about events that might happen once every few millennia. But here's what this observation reveals. The upper bounds of stellar behavior are higher than we thought. Our Sun is capable, in principle, of violence we've never witnessed. The fact that it hasn't done something doesn't mean it can't. And the fact that other stars, very much like ours, have done it, means we can't dismiss the possibility as astrophysical fantasy. The existence of superflares forces us to recalibrate our assumptions about solar risk. For centuries, we've assumed that the worst the Sun could throw at us was something like the Carrington event, a massive flare, a fast coronal mass ejection, a severe but survivable geomagnetic storm. The discovery of superflares tells us that the worst case is actually much worse. Unimaginably worse. Extinction level worse. Does this change our immediate risk assessment? Not really. The probability of a superflare from our Sun remains vanishingly small, but it does change the theoretical maximum. It expands the envelope of possibility. And in a universe where low probability events eventually become certainties given enough time, that matters. This is the cosmic context that makes our current predicament so fascinating and so terrifying. We're living through a moment where human civilization has become entirely dependent on electromagnetic technology during a period of weakening planetary magnetic protection, right as our star enters a solar maximum that's stronger than predicted, all while knowing that the Sun is capable of far worse than we've ever seen. We're balanced on a knife edge, not because the Sun is behaving abnormally, not because Earth's magnetic field is collapsing, but because we've built a civilization that requires both of these systems to remain stable, and we've done it during a period when neither system is guaranteed to cooperate. Frame this in deep time. Earth has survived worse, much worse. 4 billion years of bombardment, supervolcano eruptions, asteroid impacts, magnetic field reversals, ice ages, and every cosmic disaster you can imagine. Life persisted. Evolution continued. The planet adapted. Microbes survived the late heavy bombardment. Complex life survived multiple mass extinctions. Mammals survived the asteroid that killed the dinosaurs. Life on Earth is resilient beyond comprehension. But Earth isn't what's at stake here. Civilization is at stake. And civilization has never faced anything like this before. We've existed as a technological species for about a century. We've been dependent on electrical grids for maybe 70 years. We've had satellite infrastructure for about 50. In geological terms, in cosmic terms, we've been vulnerable for less than an eye blink. We have no track record of surviving these kinds of events because we've never experienced them while being this fragile. Think about what that means. Every previous civilization on Earth was fundamentally local. If a solar storm knocked out their compasses or created strange lights in the sky, it was a curiosity. An omen, maybe. A topic for philosophers and priests. But it didn't collapse their food distribution networks. It didn't destroy their communication infrastructure. It didn't leave them unable to pump water or treat sewage or refrigerate medicine. We are the first civilization in Earth's history where a cosmic event happening 93 million miles away could cause cascading failures that end our way of life. We are the first generation where space weather is an existential threat. There's something almost poetic about the timing. We reached our technological peak, our maximum dependence on electromagnetic systems, our greatest vulnerability to space weather, just as we're entering a solar maximum with a weakened magnetic field. It's like evolution scheduled a stress test. Like the universe is asking, okay, you've built this impressive civilization, but can you maintain it when conditions stop being ideal? The timing feels almost deliberate, though of course it's not. The universe doesn't schedule catastrophes. It doesn't care about human drama. But the coincidence is striking enough to make you wonder whether there's some deeper principle at work. Whether civilizations tend to become maximally vulnerable right before they're tested. Whether technological development inherently creates fragility before it creates resilience. Let me take you on one final tangent, one last piece of cosmic context that ties this all together. In 2019, astronomers detected an object called 2I Borisov, the second confirmed interstellar visitor to our solar system. Before that, in 2017, we detected Oumuamua. These objects came from other star systems, traveled through interstellar space for millions of years, and briefly passed through our neighborhood before heading back out into the void. They're not threats, they're messengers. They're physical samples of other stellar systems, other planetary formations, other cosmic environments. And they remind us that our sun, our solar system, our planetary magnetic field are all part of a much larger story. We're one star among billions, one magnetic dynamo among countless others, one civilization trying to figure out how to survive in a universe that doesn't particularly care whether we do. The interstellar objects reveal something profound about stellar systems. They're dynamic, they're violent, they eject material, they evolve, they change. Our solar system isn't frozen in time. It's an active, evolving system. And we're trying to maintain a stable civilization on a planet whose protective mechanisms are themselves evolving. Oumuamua was particularly strange. Its elongated shape, its unexpected acceleration as it left the solar system, its lack of detectable outgassing. It behaved like nothing we'd seen before. Scientists still debate what it was. A comet with unusual composition? A fragment of a shattered planet? Something else entirely? We don't know. We probably never will. It's already too far away to study further, racing back into interstellar space at tens of thousands of kilometers per hour. But what Oumuamua and 2I Borisov taught us is that interstellar space is not empty. It's full of debris from other stellar systems. Rocks and ice and who knows what else, wandering between the stars, occasionally passing through planetary systems like ours. Each one carries information about its origin. Each one is a sample of another corner of the galaxy. And each one reminds us that we're part of a much larger, much more violent universe than we usually consider. There's a final, haunting thought that I keep returning to. Human civilization emerged during a period of exceptional stability. The past 10,000 years have been unusually calm, climatically, geologically, and cosmically. We built agriculture, cities, nations, and global infrastructure during peacetime. We assumed peacetime was normal. We designed everything around the assumption that conditions would remain stable. The Holocene epoch, the period since the last ice age ended, has been remarkably stable compared to earlier periods in Earth's history. Temperatures have varied, yes, sea levels have changed, but the swings have been relatively modest. No supervolcano eruptions, no major asteroid impacts, no extreme solar activity, just enough stability for humans to develop complex agriculture, then cities, then trade networks, then industrial civilization, then the global technological society we have today. We won the cosmic lottery. We got 10,000 years of good weather, geologically speaking, and we used that time to build a civilization that depends on the good weather continuing forever. But stability is the anomaly. Change is the norm. And we're about to find out whether a civilization optimized for stability can survive in a universe defined by chaos. The technological peak we've reached is impressive. The knowledge we've accumulated is staggering. The systems we've built are marvels of engineering and cooperation, but all of it, every satellite, every power line, every GPS receiver, every piece of technology that makes modern life possible, depends on conditions remaining within certain parameters, depends on the sun behaving, depends on Earth's magnetic field holding steady, depends on near-Earth space remaining stable. We handed the sun leverage over our survival without really thinking about it. We made ourselves dependent on its good behavior without a backup plan. And now, as the next solar peak arrives, as our magnetic shield weakens, as our models fail to predict what happens next, we're realizing that maybe, just maybe, we should have been more careful. The sun doesn't need to take anything back. We handed it everything. The only question now is whether we have enough time to take some of it back before the bill comes due, and whether we'll even recognize the bill when it arrives.